Welcome to qnawire.
You're told that you have an astronaut that's moving in a certain direction relative to a spaceship here. So let's just take everything relative to the spaceship in this case. So he's moving with 20 meters per second, and the astronaut with equipment, the total mass is 150 kilograms over here. So you know that since this is the initial case, the total momentum that he has, pi, is actually equal to 150 kilograms times the 20 meters per second, which is 3,000 kilogram meters per second. So this is the total momentum that he has before. Now, in order for him to go back in opposite direction, it means whatever he's throwing away needs to provide momentum that's equal and opposite to this. And even so, let's say if you want, let's see how much momentum he will need if that's the case. So P final has to be also 3,000 because momentum is always conserved in this case because we assume that him throwing things off is some type of collision or some type of collision that we can analyze as a collision. So in this case, the PF must be equal to m, the mass of the astronaut, um, times his velocity plus the mass of whatever equipment that he loses times its velocity. So that's what needs to account for the 3,000 here. But we know that the total mass in this case can only be 150. So the total mass in this case can only be 150. And the maximum amount of velocity that he can have here is going to be 5. So this can be the mass of the astronaut times velocity of the astronaut plus mass of the equipment that he has to lose times 5, essentially. But we know that the mass of the astronaut and mass of the equipment are related because total is 550, is 150. So this is 150 minus the mass of the equipment times the velocity of the astronaut plus. So this is the mass of the equipment or 5 times the mass of the equipment. So this is essentially the equation that should give you 3,000. So now you can look to see what you can simplify here. So notice that if this astronaut, let's say he loses about 5 kilograms worth of equipment, right? So this would be 145 velocity of the astronaut plus 5 m/e. But notice that for him to go back the opposite way, this equipment needs to be going the other direction. So it means that this should actually be a negative in this case. So this should give you 3,000. And then the mass of the equipment is again 5. So this is now 25. So that here is 25. So in this case, so if you move that 25 over here, you divide, you'll notice that, so that would be 3,025 divided by 145. So that will mean that this astronaut would need to be, so his velocity would need to be something like 20.7, which is greater than the initial here. And So essentially, so now you realize that the only way this can happen is if he goes faster than he did before. So essentially, so let's look at some limiting cases here. So if in order to accumulate this much momentum here and by losing his equipment over here, he needs essentially the amount of mass that would be required. So let's say this is 5, because this is essentially so that's the speed, the maximum speed of the equipment that he can. So this would need something like 600 kilograms of mass in order to arrest all the momentum. So in order to give you momentum in the opposite direction, you would need to account for this 3,000 here. And to get to 3,000, you need to lose 600 kilograms of mass. So already you can even see just by this analysis here that this is clearly too much weight. So you cannot even hope to accumulate this much momentum by throwing things away, because again, it's going to need way too much weight than he has initially. So in order to account for the initial momentum of the system, the mass that needs to be gotten rid of is too large, or is larger than the initial mass of the system. So clearly this situation cannot